Hello, everybody. I hope you're doing well. Um, at this point, I should be well out of surgery. Things should be recovering, and we should all be doing okay. We had started talking about Neidhart's equation in class on Friday, or sorry, not Friday, Wednesday, and I wanted to return to it now so that we could understand it for our own homework. So, what we had was this differential equation, dn dt is equal to Rn. And again, what we saw in class is this was saying that the rate of growth was directly proportional to the number of objects that you had. Right? And this is a seemingly simple equation in many ways. It says that if I have 10 times as many cells, my rate of growth will be 10 times what a single cell would be. And I recognize that some people think that's very intuitive. But this is a rather profound difference. This is a very different kind of equation than others you may have encountered before, right? You're often used to thinking about the derivative of something when it's a polynomial. So if I've got d dt and I have a function that's like t to the sixth, then that is now going to be 6t to the fifth. And this derivative is not the same function I started with, right? It is a, quote, smaller function. I have reduced its power. What's really magical about the exponential is that when you take the derivative, you get the same function back. And so now let's look at that in a little bit more detail, right? And that's what this is saying here. The function solution is the original population times an exponential function. So let's see that in action, where that came from. Okay, so this should just be what we saw in class on Friday. I just thought, hey, let's cover it again, make sure that we're all on the same page. And what we're saying is that the solution to the differential equation can be found by this, where n naught is just your starting population, and then e to the rt, which is sometimes written as exponential rt. There's literally no difference between writing this versus writing this. It's just a preference. But, you might see both, so I thought you should see both. So we're saying that n is equal to n naught e to the rt. Well, when I take that derivative, if you remember, the derivative of e to the x, right, d dx of e to the x is just e to the x. That's the amazing part about it. When you're looking at an exponential curve, any given value is its slope. And that's what's really profound, is the exponential is the function in which any given value is its slope. So it gets a little bit more complicated if you've got something else in there. Not a lot, but a little bit more complicated. Let's say you've got d dx of e to the ax. Well, in that case, we're now looking at a e to the ax. All right, so that's a slightly, apologies if it was a little bit hard to hear me at the start of this video. I just realized that my microphone is in the wrong spot. So I don't do a lot of recording down here, but we are. Okay, so hopefully you can hear me better now. And if the start of the video was loud, I'm sorry for the volume, or it was quiet and you made the volume louder. I'm sorry for that transition. But we'll try not to do it again. Okay, so when I have e to the ax and I take that derivative, what I get is e to the ax again times that a in front. Let me move this out of the way so we don't have any confusion. Right, so the derivative of e to the ax is still e to the ax, except now with the chain rule, I pick up that extra factor of the a. All right, so now we come and we look at our equation. We say, okay, calculate the derivative. I calculate the derivative of that. The only thing that's a variable is time. So n naught doesn't change. My exponential returns an exponential. I get the original argument up top, and then I take the derivative of what's here, consistent with my chain rule. In that case, I just get r. And so now we just get this equation. But if we're looking carefully, we realize that this is just the original function n. So I can now say that dn dt is equal to Rn, which is the original differential equation that we were solving in the first place. Now, some people like the solution given this way in terms of an exponential, and other people prefer it to be written in a different exponential base. That is, they prefer it to be written with the base of 2 because they want to think about how often something is doubling. Well, this is not a new solution. We simply solve it, or we simply manipulate the original equation that we had, which is this n naught e to the rt, to be in terms of 2. So how do I do that? Well, this right here, if I were to simplify it, 2 to the log base 2 would just go away, leaving me with e to the RT. So you may not have ever thought to do this, but this is basically like, exponentiating this thing without changing it. And so the reason, again, we're doing this is we'd like to think about this in terms of growth of powers of 2, 2 to the 1, 2 to the 2, 2 to the 3, as opposed to exponentials. And so when I do that, I now, in the numerator, in the exponential, have this log base 2 of e to the RT. Well, with my log rules, I can take the powers of RT and put them out front. So now I have the original population times 2 raised to all this stuff, right? This is all in the exponent. So I've got some rate, I've got my time variable, and then I just have a number, right? That's all that is. It's log base 2 of e. It's about 1.4. Well, some people like this form to be even simpler. That is, they don't want to look at all the stuff in it. So they define a new variable. And the new variable they define is often called tau. And tau is referred to as a time constant for reasons we're going to see in just a moment. And so they define it as all of this stuff, but inverse. They put it all in the denominator. And it actually leads to kind of a nice result. What it looks like is something like the following. So we take all that stuff, we put it in the denominator, and we get the original population 2 to the t divided by tau in the exponential. And why is that? Well, that allows us to use the fact that tau has units of time. Why does it have units of time? Well, I can't have like meters or seconds in my exponent. I have to be unitless. So we know that all this stuff has to have units of inverse time. And so I now have something in terms of that tau unit. Now, what do I mean by that? Well, let's imagine I was looking at time equals 0. Well, if I do that, I just have n equals n naught. That's my original population. Not a shocker. Let's, instead of saying time is like 1 second, I'm going to say time is 1 tau. So whatever tau is a number I know. It's some number of seconds. There's hours or minutes or whatever. And if time is 1 tau, then n is now 2 n naught. All right? So when time is 1 tau, this just becomes 1. And so I get a factor of 2, and there I go. So what's my doubling time? 1 tau. Well, let's keep going. Let's say that time is now 2 tau. So that should be 2 doubling times. And what we see there is n is now equal to 2 squared n naught, or 4 n naught. If t is equal to 5 tau, now that means n is going to equal 2 to the 5th times n naught. And so that's going to be 32 times the original population. So some people really enjoy the tau because it lets them think directly in terms of doubling time. It's still exponential growth. It's still e to the x. You haven't changed anything. It's just you put it into a unit that's a little bit easier for people to see and visualize. So why didn't we list that equation here? And the truth is, taking the derivative of that is harder, right? If I said to you, let's calculate that derivative, you might say, oh, I remember I did that at one point, but I don't remember how to do it anymore. And that's the truth. You did it at some point, you remember how to do it anymore. And what you did when you wanted to actually take that derivative was you took the log of each side and then you took the derivative, because the log let you get rid of the 2 and bring the powers into the denominator, or into the coefficient, and take a derivative. So we're going to work with this equation in this form, but I wanted you to see it in terms of a population growth dynamic. And that's what most people who think about growth think about an equation that looks something like that. But we're not content with this equation. This equation assumes forever growth, right? And we're not talking about housing prices, right? Because they only go up. That is sarcasm. This is an assumption that we only have population growth. And it's not a bad model, it's just not a realistic model, right? I'm a physicist. We can have great models that don't fit reality, and we're okay with that. So this is a really good model over a period of time. But let's make it now more complicated. Let's say instead we have some kind of death or loss or decay or breakdown in our thing. Well, the original growth equation was given by that. That's dn dt is Rn. But now we want to look at this not just in terms of forever growth, but we want to have degradation or loss. And so we can modify that differential equation as such. And just to be clear, this is probably straightforward, but let's just make sure. If I were to multiply this out, it would be Rn squared divided by k. And so we still have our exponential growth term, but we now have something reducing our rate. And this Rn squared over k is the thing that's reducing our rate. And you might say, how would I possibly know to do that? The truth is there isn't an intuitive answer. The truth is you try stuff until something matches your data. What is it that matches your data? This thing, right? This is the kind of thing that matches your data. In science, we often try to find the answer no matter what. We just keep busting until we get the right answer. Then we try to figure out like later why it was an obvious thing to do. And then unfortunately, many times we act like it was always obvious. I'm trying not to do that. I'm trying to say, here's what we do. It works. And now let's see if we can understand it. So what's really interesting here is this modification now says something really cool. It says I can have growth, but it also says I can have decay. And I can be growth dominated, which would be if this term is larger, right? If 1 is bigger than nk, I'm growth dominated. If n over k, however, is bigger than 1, I'm now decay dominated. And so what you actually get in this sort of system is an equilibrium that forms. You either get this growth pushing you towards n, or you get this decay dragging you back to n. And that's what is happening now. And this looks pretty much like the same equation, right? But we've just modified it a little bit to allow there to be degradation. And so that's what's going on here in this chunk of the book. I wanted to get that up there because it is a little bit dense to read. I know some people are already a little bit frustrated with this book saying it's just too much. And I'll tell you this, the authors have heard that. I've talked to them about it and they agree that it is too much. They just, they don't have a good way of fixing it yet. You know, there's so much they want to say and so much they want to share. It's a little bit tough to figure out what to get rid of and what to keep. Because the book is already pretty thick, right? And, you know, they don't want to get rid of stuff, and I can totally appreciate that. So when we then look at how do I solve this equation, we're going to get something that's a little bit more complicated. And we're just going to take that solution right now to be true. And if we look at this, we say, oh, look, there is the original solution I started with. But now it turns out there are these extra terms that have appeared. So these extra terms have come about because of the interplay that happens in this. And you can check this just like we did before. You take n of t, you calculate its derivative, and you will see this appear. It's going to be a little bit more complicated because you've got numerator and denominator stuff. And so you might have a product rule, you might have a quotient rule, depending on, you know, what feels better for you in terms of calculus. But you can see that had we written this in terms of twos, then we would have taken logs, and it would have been even messier, and we don't even want to do that, right? We're going to just press the I believe button and move on because there's so much that we can't take the time to learn. You have to start somewhere. So this is now our solution for what does population look like when I have growth and decay in a system. I hope this has helped you kind of understand what you're seeing and reading here. The rest of this is just understanding how to do this for any other function. So say, you know, we don't have this simple relationship. We have an even more complicated relationship. What might we do? And that's what the rest of this function is doing, is just saying, okay, let's try to figure out how that would look like, what that would look like in a different circumstance. All right, I'm going to stop the video here. I'm going to post this now, and you guys are going to have this to help you understand that homework. Thanks a lot. I hope you're doing well. Goodbye for now.